Let's continue to work on these rotational equilibrium problems, and for this video guide I want to look at problems where we have this beam that's kind of drawn in this upwards direction, and then of course we do have some angles to work with here, so these are all very good practice questions. Okay, so for this problem we have a 6-meter uniform beam of mass 25 kilograms, and it's not moving because it's being suspended by a cable as shown, and we also have an 85 kilogram object that hangs from one end. And our goal is that we need to find the tension in the cable. So I'm going to find the tension in this particular cable right there in green. Okay, perfect. So let me kind of erase some of the highlights here, and let's zoom in and start breaking down this problem here. Okay, so step number one, we want to find a pivot point, and a very good strategy is to always put the pivot point right against the wall here, and that will eliminate any forces at the wall there, and then we can go ahead and find the torques at the other key locations. After that, let's go ahead and draw the free body diagram. Okay, so since this particular beam weighs 25 kilograms, it does have a center of gravity right in the middle. So I will draw a vertical force in the downwards direction, and I'll call that FG1. And there's also another mass hanging at the very end of the beam, so I'll draw another force here, and I'll call that FG2. And of course the wire or the cable here also has a force acting on it, and we'll call that the force tension, so Ft. Alright, so there's my free body diagram for this particular case. Now when we're dealing with torque questions, what we really need is the perpendicular force that's acting at those various points. And unfortunately none of these three forces are the perpendicular components, so what we need to do now is we need to break down each force into its components and find the perpendicular force. Let's go ahead and start off with the force tension here, because this one's probably the easiest one to break down. So we do have a horizontal component there, and then we also have this vertical component, which I'll draw a little bit longer, and I'll label that as Fy. We notice that this is 67 degrees, so the angle is touching the beam, which is the adjacent side. So if I want to find Fy, then I need to find the force tension, or I need to use the force tension, which is the magnitude of that angular force, and I need to multiply that by sine of 67 degrees. So this is very similar as finding the vertical component when you're working with those projectile theory questions again. And what I'll do now is I'll erase all of this, and I just want to draw this perpendicular box here, right? So that is the component that I need to set up a torque expression. Okay, so now I have two forces that are acting in the downwards direction, and I will go ahead and draw a horizontal component there, and that means I do have a vertical component here, and I will draw this one a little bit longer here just to kind of help me write an expression later on. So this is the vertical component there. And what we're going to do now is we're going to review the alternate interiors angle concept. So if you have two parallel lines, such as this and this, then the alternate interiors angle concept states that these two angles here are equal. Okay, so how does that apply to this problem here? Well, here is a straight line, here's the side of the Z, and then here's another parallel line, right? So as you can see that these lines right here highlighted in yellow, these are the parallel lines, right? So what we're trying to say here is if this is 75 degrees, then this right here is going to be 75 degrees. Okay. Okay. All right, so with that being said, let me just kind of erase this here. Our goal here is we want to calculate this perpendicular force right there, right? So if the 75 degrees is touching the beam there, then we can calculate this perpendicular side. I'll label this as Fy again. And this is going to be equal to Fg1 times sine of the angle, sine of 75 degrees. Okay, and ironically, and since we set that up, the other perpendicular component here, I'll label this as Fy again. This is the same thing, or the same kind of concept, which will be Fg2 times sine of 75 degrees. Okay, so this angle here is also 75 degrees. Okay, so there you go. Now that we've have our perpendicular components here, let me just kind of tidy this up a little bit. I'm going to erase the free body diagram because I don't need it anymore. And there you go. Those are our perpendicular components right there. Okay, so this is what we're going to use to kind of set up our rotational equilibrium argument here. And what I want to say here too is if we're referencing everything with the pivot here, by now you should recognize that this perpendicular component is going in the clockwise direction. This is also going in the clockwise direction. And this upward perpendicular component is going in the counterclockwise direction. Okay, so if I want to go ahead and write a torque expression, I'll call this torque 1. It's going the clockwise direction. This will be Fg1 times sine of 75 degrees. And then we need the distance, right? So this distance right here is the halfway mark. So if we know that the whole beam is, I believe the whole beam is 6 meters, then the center of gravity is approximately 3 meters from the pivot. And if I want to find this torque over here, I'll call this torque 2. Well, this will be Fg2 sine of 75 degrees. So we're multiplying all that. And this actually takes the full distance of 6 meters from the pivot. And finally, we have our third torque over here going in the counterclockwise direction. That's calculated as Ft sine 67 degrees. And if I look at the diagram here, it looks like it's about 4 meters from the pivot point. All right, so that's how you kind of set up all your torque equations. And now we can kind of jump into this final expression here, the rotational equilibrium concept. So at the pivot, the beam is not moving because the sum of the torques are equal to 0. And that literally means that the sum of the torques in the clockwise direction is equal to the sum of the torques in the counterclockwise direction, right? And we had 2 torques in the clockwise direction, so I'll call that T1 plus T2. And in the clockwise direction, counterclockwise direction, we had the third torque right there. Okay, and we all know that I'm kind of generalizing here now. The torque expressions is always the force times the distance, and this is also the force times the distance. So we've already made expressions for all 3 of these torque calculations from above, so we will just kind of rewrite them again. So this expression right here was Fg1 times sine of 75 degrees, and we times that by 3 meters. The second force will be Fg2 times sine of 75 degrees, and this one is actually 6 meters from the pivot point. And on the counterclockwise side, we'll call that the force tension times sine of 67 degrees, and that's actually 4 meters from the pivot point. I think that matches up. Yeah. Okay. So here we are. That's what we need to do now is we need to convert these all into numbers now. Sorry, what I mean by that is the FG1s, the FG2s, we want to make sure we change that to mass times the acceleration due to gravity. So the mass of the beam was, I think it was 25 kilograms, right? So the mass of the beam was 25 kilograms times by the acceleration due to gravity, and then we got to times it by sine of 75 degrees times it by 3 meters. So this will get quite long. So the second force of gravity here is mass times the acceleration due to gravity. So that mass was 85 kilograms. That was the mass hanging at the very end. So 9.80 times sine of 75. And then we times that by 6 meters. And we actually need to find Ft over here, right? So I'll just kind of label that as Ft. And then we have sine of 67 times 4. Okay, so now we generally have a linear equation here to solve. So let me kind of highlight Ft now, and your job is to do all the calculations and solve for Ft. So I'll pause the video here, and then I will show you the final answer in a bit. Okay, so after all that work, the force tension should be around 1503.98, and if you want to just round that down to two sig figs, it's roughly around 1500 newtons there. Okay, so that's the final answer for this particular problem. And if I go back to my original diagram here, let me kind of erase all this. And so what we've just established here is this cable right here. The force in that cable is about 1500 newtons. And if the cable is 1500 newtons, then this whole beam will not move, and it is in rotational equilibrium. Okay, that's it for this question, and in a bit we'll move on to the next question.